COMAP, which is the Consortium for Mathematics and its Applications. And the webinar series has been going on since September. And we've had a variety of folks talking about how they incorporate math modeling in their classrooms and outside of the classroom. So that's been the focus of the webinar. And today, if you have questions, you can type them in the chat, or you can also, if you have comments, you can type them in the chat, and I'll be monitoring the chat so that I can interrupt our speakers if we need to do that, and share your questions. The other thing that might be helpful now, if you don't mind, if you want to go ahead and go into the chat and just let us know if you want to say hi and let us know where you are, or a little information about maybe your experience modeling. Have you done some little bit of modeling with your students, or you kind of have participated in some of the modeling contests? You can let us know that, and that way we can have some picture of who you are. So we're grateful that COMAP is supporting us in this throughout this year with this webinar series. And today we have David Stein and Greta Mills and Cynthia Chen with us. And they're going to talk to us about building creativity and confidence in their students as math modelers. And then at the end, we'll leave about 5 minutes so that you can ask questions. And also I can put in a plug for our next webinar. So thank you all again very much. Thank you, David and Greta and Cynthia, for being with us. We're very grateful that you are spending this time with us today. So I'll turn it over to y'all.
Okay. I guess we're going to start with talking about each of our 3 schools and what math modeling looks like in our schools. So I'll start. My name is David Stein, and I am a math teacher at Montgomery Blair High School in Silver Spring, Maryland, right outside of Washington, D.C. And we're a large high school of about 3,500 kids. And the modeling that I do that we do in our school has 2 parts. We teach a senior class in statistical research, which is really a modeling class for students who have already finished AP statistics. And it's a 2-semester class where each semester takes a different focus. Sometimes we do sports or politics or education research. We change the focus around each semester. But it's all based on students doing modeling. And then the other part is that we have a club, a math modeling club that meets after school. It's a student-run club in which the kids work together on developing teams and skills that they're going to use in modeling competitions like the COMAP competition and the HiMCM and M3 competition. So that's my school.
And I'm Greta Mills. I teach at Oxbridge Academy, which is in West Palm Beach, Florida. And at my previous school and at my current school, I've been privileged to have a standalone modeling course that comes after calculus that really synthesizes a lot of the math that the students have learned in the context of real-world modeling problems. Over the past 2 years, this has morphed into a computational modeling artificial intelligence course, but it still retains the flavor of looking at real-world problems through a modeling lens. These classes have participated in the HiMCM and the M3 challenge almost every year that I've taught a modeling class. The first couple of years I didn't get to participate. But in addition to that, we embed modeling throughout all of our upper level curriculum, from the pre-calc levels on up, with some elements of modeling in the younger and earlier years. And it's just been really neat to see students latch on to mathematics when they see the context for the math that they've been learning.
So my name's Cynthia Chen. I'm a teacher at Madison East High School in Madison, Wisconsin. We're a comprehensive public high school, but only about half the size of David's. We're about 1,800 people. We do not have a standalone modeling course. Our math modeling teams are an extracurricular group. We meet once a week and we compete in 2 or 3 competitions a year. And the club also presents their papers to other classes in a STEM week guest speaker series that we have each spring, at least in a normal year. But then we do try to incorporate the principles of modeling and the skills from modeling into our classrooms, into our instruction. Right now, for me, that would be Calculus AB and Algebra 2 level work, but we have had students on the teams who are as novice at modeling and at the level of their career at the beginning of their math careers in high school. So they might be Algebra 1 students in 9th grade. We've had those students participating in the math modeling teams as well. So we can fit this in anywhere, and we try to do that. So I'll talk about this one. What is the difference between a word problem and a modeling problem? And so that's this is an example of where you can take anything from Algebra 1 on up and look at those modeling principles. So this is a classic word problem. You're given a lot of facts, so we'll just add all the facts in there, David. Okay, and there's pretty clearly, as you read through this, it's fairly prescriptive. Most of us could figure out right away what we need to do to get an answer, and there's one answer. So there's an answer key that could be provided for this question, and our younger students, even our older students, are very comfortable with this idea that there's one way to do it and there's one right answer. So let's move on to what a modeling question would look like. A modeling question is much more open. So any town, you don't know the population of the town, you don't know how much waste they're producing, you don't know what materials are being collected in this particular town. And you're often also asked a very utilitarian question in the sense that not only is there a numerical answer, but there's some sort of evaluation or value placed on the answer. How successful is this program? Do we need to change it? Can we modify the program to get better results? And how do you measure those results at all? So at this point, students, you're asking them for an answer, but they might have, I think there's one more bullet there, David. They will probably have a lot of questions. So that's kind of the key to this, is that there's no answer that everyone's going to come up with the same answer. And in fact, before they can come up with any answer, students are going to be asking a lot of questions, and they're going to be asking questions about all the constraints that we left out. And they may be able to find constraints, either research it or they may make some assumptions about what the constraints are. And that opens it up for a very low floor, high ceiling approach, because kids can bring their life experience to this. Any idea to start out with is fine. There's no right answer. You just dive in and really explore the problem before you try to answer it. And again, when there's no right answer, at first it makes kids nervous, but once they get used to it, they have a lot more confidence because they realize that it is also their job to validate their answers, and they like having that sense of control. Okay, I think we can move on. So this is an example that I often use with students just to talk about how to be creative and to accept the freedom that modeling gives you. This one's kind of a joke. It was from a newspaper article in the New York Times. It's called the Celebrity Divorce Formula, and it has to do with what are the odds that a marriage will last for a certain number of years. And so what happens is that you list all the things that might be factors. And so you can see there's a long list of possible conditions. And then you try to figure out, how do those factors interact? Should they be squared? Should they be positive? Should they be negative? Should they be in the denominator? Should they be in the numerator? And that kind of thinking is very mathematical and has to do with understanding the structure and behavior of formulas. Maybe you try and graph a relationship to understand how things are related. But there's also something very free about this, because choosing the variables is up to the inventor of the formula, and experimenting with the structures is also up to the inventors, although hopefully they have some real world experience that comes into this. So as David is illustrating, we have the idea of defining your variables and producing meaningful units, giving a domain and range, understanding the type of relationship the variables might have. And then I think there's a number 4 there. Defining the output, like what are you actually producing? Are you producing a probability? Are you producing a rank? Are you producing some kind of decision? Do this, don't do this, or a decision criteria. And kids have a lot of freedom to play with that. And so there's the creative piece. And once they understand that they are allowed to make this what they want to make it, as long as they can back it up, it becomes a lot of fun. And they, again, feel like they're exercising both creativity and developing confidence. I think we can go on.
Vincent, I would add in, I'm just thinking as I'm looking at your formula here, the effect sizes,
Yes.
the multiples that they're putting on, and the shifts that they're putting into the denominators here are all, decisions that the modelers have to make and be able to justify too.
So as freeing as it can be to look at a real world problem and give students the opportunity to develop their own formulas, within that, there's still a structure that can be followed. And we sometimes call this the math modeling cycle or the math modeling process. This graphic comes from Math Modeling Getting Solutions, put out by CIM. And there's similar ones in the modeling world that talk about this iterative process where you start with a real world problem and you play with the problem. You look at what is known, you look at what questions you might have about what is known. You might have extraneous information, you might have a very ill-defined problem. And part of the process in modeling is that you need to come to an understanding about what it is you're looking at and what it is you're trying to find. And so I really spend quite a bit of time with students in developing this process and giving them the opportunity to discuss, what are some of the important features of a particular problem? What are some of the things that we can ignore safely? Why can we ignore those? What research is out there that can support some of the decisions that we're making? And it really is very iterative, because as you start to refine your assumptions and you define your problem, you end up finding out that you've got more questions and more problems that need to be addressed. So at each step of the process, you're always stepping back and asking, is there information that I'm missing? Is there some nuance to this that isn't embedded in this problem? Are my assumptions valid? And this really gives the opportunity for students to really dig deep into a problem and to play with it without the fear that they're not getting the right answer. And it gives them the opportunity to collaborate with each other as well, which I think is a real strength of modeling. It's not a solo sport. It really is a group activity. And the more you can bounce ideas off each other, the more you can learn about your understanding of a problem. And oh yes, thank you for the link to the modeling handbook, Maria. And one of the things that I like about this is that, not only do you end up getting some kind of a solution that you can then analyze, refine, and revisit, but there's also an audience. So there's somebody to whom the answer to this question is really important, and it's not your teacher. It might be somebody who has to make some real decisions about something. It might be, your local government has to make decisions about recycling or something like that. So the more you can give a real world context and real value to the problem, the more that report is going to resonate with your students as well. And I think this gives us a nice opportunity to maybe look at a specific problem. So we can, I think, go to the next slide, David. Thank you. So one of the questions that I often hear is, where do you get your problems from? Where do you find real problems? And when you've been at it for long enough, you can find problems in your own backyard. We've done a lot of problems that pertain to my school that are actual decisions that my school has to make. At my previous school, we had a problem with, what lunch program we were going to administer at the elementary level. And the school board actually came to the modeling class and posed this question. You know, we're struggling with handling lunch and lunch money and lunch menus and just putting it all together. And the modeling class took that as a challenge and addressed it, and they're still using the recommendation that one of the teams made at that school now, you know, and that's 15 years later. But if you're just starting out, it can be really daunting to try to find something that is actually going to turn out to be a robust question. So I find that the modeling competitions, COMAP and HiMCM, they have a rich repertoire of problems. The very first problem I ever participated in, that my students ever participated in, the very first competition was the COMAP high school mathematical contest in modeling in 2004. And the problem that my teams faced is actually one that we're going to be delving into a little bit now. So I think we can move on to the next slide, David. Thank you. So this is the art gallery problem, very first problem that my teams ever faced. And so I've got the perspective of having gone through this as a contest problem, and then also having looked at this as a standalone problem that year after year my students can address at various levels, you know, of their mathematical journey. So I've looked at this within the modeling class, and I've also looked at it from a pre-calculus trigonometry class. So this is the scenario. We have these two layouts of an art gallery. The art gallery has fixed dimensions, but it has portable walls. Those walls can be arranged in multiple configurations to display different paintings. They come in 5-meter sections. There are entrances that are on opposite corners, and then there are cameras that are on the remaining opposite corners. And the corners have, the cameras have specific angles of vision. So I think it's a 30-degree angle that they can take in, and they also rotate from one side of the room to the other. And it takes a certain amount of time to do this rotation. So how do we want to lay out the painting so that we can have maximized security, but also something that is aesthetically pleasing as an art gallery should be? So we can go to the next slide. So what I wanted to do is just demonstrate the range of thinking that students can demonstrate by looking at a problem such as this, and not just in terms of the way that they approach the problem, but also the mathematics that they start pulling into the problem. And you'll see a wide range of mathematics. This is courtesy of a colleague of mine. You know, she also has done this problem multiple times over the years, and this it's a lovely diagram. They used all sorts of trigonometric formulas to look at, you know, the camera, the angle, being the line of sight over the portable wall, etc. We can go to the next slide. And another group decided that they were going to use their calculus knowledge by looking at determining the amount of security based as a limit of, I think this is an average value, the average number of paintings seen per second. So yeah, completely different approaches, one using trigonometry, one using concepts from calculus. Next slide. And then in my classes, one of the things that the students were really struggling with was visualizing what was going on. So, you know, back when dynamic geometry was really new and exciting, Geometer Sketchpad was all the rage. I'm really dating myself now, and I know that. I had students who decided they wanted to try to model this visually and get a sense of what was actually happening with the cameras. So they created a layout in Geometer Sketchpad with dynamic cameras that could move. And this is just one tab from student work. This must have been in, I think, 2009, with all the information that they are using for this particular problem. So they've got some kind of a key. So they've got unwatched wall measurements, they've got field of vision, they've got minimum distance from a blind spot to the door. So they're considering all these different things. And then they also modeled it with dynamic motion. So David, we can go to the next slide. Thank you. And so that should go on its own. Yep. So they just wanted to understand with each layout what exactly the cameras were seeing. So they created you know, something dynamic that would show how that field of vision looked as it was sweeping, doing one full sweep. And they use that to calculate different percentages. So unwatched area, unwatched wall space, etc. Next slide. And they apply that to the two given configurations from the original problem. So one had fewer blind spots and was clearly more secure, and the other one was really not secure because it had quite a lot of blind spots. And then they had to create their own configuration. We can look on the next slide. And with each one of these configurations, they're looking at refining their metric. So how did they incorporate unwatched area versus unwatched wall space versus the amount of time perhaps that a painting is visible. I think we can go to the next slide. Oh, I had one group that decided that when Google SketchUp became all the rage, then they decided they wanted to model it in 3D so they could get an even more robust feel for what was going on. So, and another group that they use their computer science knowledge to create basically a 3D rendering of the art gallery, and they made it a playable video game. So they tested their model by having people play the video game, and the player takes the part of the art thief, and they have to navigate their way to a painting and try to get from the painting to the door without the camera seeing them. And so a secure art gallery would mean that you lose the game, but you win at security. So the final score is you want a lower score for greater security. And that was probably, I want to say that was about 10 years ago or so, probably longer ago than that. So they were really very forward thinking in their use of programming to try to figure this out. And they turned it into a game, which made it, that just brought it to a whole new level. Next slide. Oh, it's on the video. There we go. And then one year I decided that I wanted to introduce this problem into our regular pre-calculus level. So these are students that really up until pre-calculus, they had been learning really algorithmic thinking, dealing with algebra 2 as a set of procedures and not really thinking about the application. So from day one, we started incorporating a lot of modeling strategies and trying to develop a modeling mindset. And to make it a little bit more accessible to the students, and this is something I might also recommend for teachers, if you modify the problem and make it a little bit more bite-sized and maybe a little bit more direction for students, it can scaffold this process for developing that modeling mindset. So rather than give them both configurations, I just reduced it to one, and we really delineated what the task was. What does it mean to be secure? How do we consider the impact of the motion of the camera? How do we use trigonometric formulas? So it was in a unit on trigonometry. So it was very specific that trigonometry should factor into this. And that I did narrow down a little bit of the options for the flexibility within the modeling process. But for these students, it was a necessary first step. And use your metric to determine the security of the previous exhibit, and then create your own layout. And then they had to create their own metric, and coming up with your own formula. It is very daunting, and it is freeing, but also intimidating at the same time to be told that, yeah, you can make up any formula you want. You just have to be able to justify the values that you're using and the way that you're combining those different criteria. Next slide. And then just additional required elements to really discretize it. Instead of looking at the camera as being a continuous motion problem, we looked at specific time values. So I think it was 4 specific times. Yeah, it says 4 specific times. And at those particular times, what was the security of the art gallery? And then this idea of technical writing a summary that communicates to your audience what it is that you were investigating, how you approached it, and what your results were. And this idea that it's more than just showing your work, it's about communicating to your client or to your audience what it is that they need to be making a decision about, or they need to be understanding. Okay, next slide. Oh, yeah. And then we had some very low-tech approaches. This was also from my colleague Lauren, but I also have had students who just took a cardboard box and cut it into the right dimensions and they had a little viewfinder and they created a little 30-degree line of sight, and they could rotate that little 30-degree line of sight so they could actually physically see as if they were the camera. So there were some really creative things that students did to wrap their head around what was going on with this problem. And it does not have to use technology. It can be very, very low tech. It can be pencil and paper. It can be trigonometry. It can be geometry. They can sketch in triangles and calculate areas by hand that way. It does not have to be super high tech. So there's really, I mean, this really truly is a low floor, high ceiling kind of a problem, because we can get all sorts of students engaged in a problem such as this. Next slide. And then this is just showing the 4 or 5 different time values. So they had tasks for each one of these time values. And the trigonometry that they used might have been right triangle trigonometry if they were considering the wall space. So that becomes a linear measure as opposed to an area measure. You could use the law of sines, law of cosines. If we're looking about the percentage of the visible floor space, then we might be using area formulas. So it really, depending on what they decide is important in their metric, we could be looking at a wide range of formulas and approaches. Next slide.
I'll just add something to Greta's observation about how these problems can go to all levels. I had one year a team of students that had finished calculus and were determined to use calculus on a particular problem. It was about the design of an airport.
Yes.
And they came up with their formula for it, they were minimizing the amount of walking that you have to do in the airport. And they came up with that the design of the airport should be a 17-sided polygon. And they insisted that that is what it had to be because that is what calculus said. And, you know, thinking of architecturally what that would mean versus couldn't you just go to 18 or at least? So it's interesting what kids will try to do, and sometimes you do have to talk them away from trying to use the most complex math possible. It's really about understanding what you're doing and making it understandable to your audience, including any architects who actually have to use your plans.
And I'll piggyback on that. I've had students in the modeling class participate in the HiMCM contest over the years, and this one year that I was doing modeling with the pre-calculus class, this is regular level, this is not our honors level. I had a team of exceptionally engaged students. They might not have been mathematicians in the purest sense, but they were very engaged by the material, and I had them also create a team and participate that same year, and they beat about 2/3 of my team. And the math that they used was very appropriate for their level. And I use that as an example that, you know, higher math is not necessarily better math. You know,
Right.
You have to use the math that's appropriate for the situation.
Right. So these few slides are going to talk a little bit about other ways that you can incorporate modeling. Greta mentioned taking problems out of the newspaper, local decision-making, or in the school decision-making within the school district. And then she talked about taking pre-created problems from various contest resources. These couple slides are about, you have curriculum that you feel is important to cover and that skills that you want kids to have. How can you add modeling into the curriculum that you already have versus going to these outside sources and pulling in problems that maybe don't line up exactly with what you're trying to teach. So this is a protocol that was shared by some colleagues of mine in Wisconsin, starting with a math problem, move it into a word problem, then it becomes an application problem, and finally it becomes a modeling problem through the use of interpretation. So the next couple slides just illustrate that and with a simple task. So this is what we'd call a naked math problem. Solve this system of equations. And we've all assigned these probably, or seen them for sure. And then we'll move on to the next level. We embed that into a context, but this is still somewhat prescriptive. You see all the numbers are there. The general structure is fairly clear. There's going to be a single answer to this and likely a small repertoire of approaches. But then we can open this out further and give that, which is very open. You might wait to do this until they've used some of the tools so that those tools are in their toolkit and would occur to them. But you can see that there's definitely some brainstorming that students would have to do here, some assumptions they would have to make, and so forth. So they will probably come back to the skill that was the same skill as the naked math problem, but there's a lot more much more fluid nature to this, and you can build those extra modeling skills, those softer inquiry and reasoning skills come into play as well. You can go to the next one.
So one of the things that I like about doing modeling is with my students is that it really allows students to feel like they have the ability to make real meaningful decisions. We have done a couple of school problems at my current school. It's a very small school, so the students really are very much a part of the community, and they know everybody in the cafe. We had a lunch line issue with congestion at some of the various stations, and we addressed that as a class. We came up with some recommendations. They've taken some of our recommendations. They haven't taken some of our recommendations. Then the pandemic happened and everybody's eating in their classroom, so nobody is congested. There's no congestion in the cafeteria anymore. But it gives them the opportunity to feel like they have some stake in a decision. What I love about modeling also is that, you know, you can be an Algebra 1 student, you can be a calculus student or beyond, you could be the top calculus student, you could be a student who struggles in calculus, but everybody has something that they can offer. So, you know, if you've got somebody who's a good writer, they can be the person who writes the summary. If you've got somebody who knows code, they can participate by writing code. So there are a lot of ways for a student to feel like they're engaged with the problem without feeling like they have to know everything about the problem. Yeah, the students, if you hook the students with the problem, they're going to want to work on it. You know, if it's just, you know, do the 1 through 50 multiples of 3, they're not going to want to do that kind of work. But this is something that is of genuine interest and perhaps something that is meaningful to the students. You know, if you engage them with something that matters to them, they're going to want to work on it. And then, yeah, how many projects have we given or have we seen students do where their audience is their teacher? So when they start writing for the teacher, they're writing for the grade, but when they're writing for the CFO of your school to try to convince them to invest in new hardware, new machinery for the cafeteria, they are much more compelled to write in a meaningful way. It validates what they're doing. It gives them the opportunity to have a voice in the decision, and you know, they're really writing something that could change the way the school is functioning, or their town, or their community. I think there might be one more, but I'm not sure. Yes, and once I started doing the modeling mindset with my pre-calculus class, this is a class I had taught for years, that every year kids would, it was like dragging them through the math because they just were not invested. And every year there would be students who would say, I don't understand why I'm learning this. Why do we have to know this? I literally did not have a single student ask me that question when we approached the same curriculum through the lens of modeling. By giving context to what they were learning, they didn't have a leg to stand on. They knew why they were learning it. It's because it was important to being able to address these real scenarios. It completely changed the way the students approached the class. It was electrifying for me. So, next slide. Oh. And the Common Core, I love the Common Core for including modeling, and it includes it both as a conceptual category and as a mathematical practice. So I like that it's its own thing, but also embedded through everything else that we do in our curriculum. And yeah, it's been something that, you know, I thread throughout all of my courses for the same reason.
And I guess what I would mention with this next slide here is, at least when the Common Core state standards were first rolled out, modeling was one of the ones that people had a difficult time getting their heads around what it meant and how they would do it and how they would assess it. So this is some statements about the math practice and what mathematical modeling really is. And I hope that these highlighted points, problems arising in everyday life, making assumptions and approximations to simplify a complicated situation, identifying important quantities in a practical situation, mapping the relationships, analyzing the relationships, and interpreting the results and reflecting on whether the results make sense, having the results serve a purpose. I hope that you've seen those things in what we've talked about so far. I really appreciate having something concrete to hang my hat on in terms of addressing this math practice in my classroom and in our extracurricular work.
So, so I've been teaching this standalone class in modeling for 15 years now. And so I've changed a lot in my approach to it as I watched the students and thought about the pedagogy behind what I'm doing. We started with 5 kids who wanted to do a class in baseball statistics, and 15 years later, I can have up to 100 kids who sign up to take this class on any given semester. And so I thought about some things that I've learned over the years of doing it. The first one is all work needs to be group work when you're doing modeling, in my view anyway. Not only because it makes it a more manageable task when students are working together, but the collaborative aspect of it is a key part of the learning in my view, because they have to be making these decisions as they go along on what their variables are, what their effect sizes are, what models they're going to use, what their assumptions are, and all of those need to be bounced off people. So I believe this firmly, that if you're going to do this, all of it should be group work. And I think Cynthia said this before, but I tell the kids nobody can do everything, but everybody can do something. And I get kids in my class with various skills, particularly around coding. I will get kids in my class who are extremely advanced coders, and others who have never done much at all. I think at the beginning when I was doing this, I was really focused on that. I had to make sure everybody knew all the coding parts that were going on in the projects. And after a while, I realized that doesn't necessarily have to be the case, is that there can be pieces of the work for everybody where everybody is learning and everybody is learning about the process, and people can focus on different aspects of the process. So nobody can do everything, but everybody can do something. I like to find projects where they can actually see if their models work. And so I'm going to show you one in a little bit about the 2020 elections. But one thing I like is when they actually can test it. I do a big project which we just finished on the NCAA basketball tournament, and when they can at the end see how their model does, I think it adds a whole lot of excitement and realism to their work. I think this is the 3rd or 4th time we've said this in this presentation, but we should look for work that they are interested in doing. And the good part about math modeling is anything can be modeled. And so if they're wherever their interests are, we can find projects and modeling opportunities for them to work on. And so yeah, go with where their interests lie. This has been a big one for me. I think as a teacher, I really struggled at the beginning of doing this on how to assess the students. And I was very focused on what was an A and what was a B and all that. And over the years of doing it, I've relaxed my views on it. And I stopped really thinking about myself as a grader in these, and instead of as an editor. And I work with them on their projects and what it should be. And it goes through an iterative process so that at the end, they have a quality piece of work that represents a thoughtful model that's well communicated and so forth. And that may require back and forth between them and me several times before that happens. But I found that to be such more effective way than for them to turn in something and me decide whether it's an A or a B or a C, whatever. So I really have started to think of myself as their editor instead of their grader.
David, can I add one point to that?
Sure, please.
So I'm going to insert one of my favorite quotes because it comes from someone who was affiliated with our local university in Wisconsin, a statistician named George Box. And his quote is that essentially all models are wrong, but some are more useful than others. And so along with David's comment, if you can help the kids understand that there is no perfect answer, there are well-defended and well-vetted answers, but there is not a single answer that you as teacher is looking for. And so they are not getting all absorbed in the game of trying to figure out exactly what the teacher wants. They're looking at their broader audience and they're allowed to use their creativity, knowing that there are going to be things that don't work out well, and that's okay. It's even better if you can identify where things don't work out well and why they're not working out well. But again, that idea, as David mentioned, that it's not about getting the exact answer and the perfect grade. It's about a quality product that you yourself understand, and as David's about to say, that other people can understand as well.
Right. Yeah, so the last part is, and you've seen this in all the slides we've talked about, is communication has to be a big part of the assignment. How they write it up, how they explain it, the visuals that they use has to be a huge part of the assignment. It cannot just be create this model and, run some simulations. Instead, it has to be, how can we explain what they're doing? And I try to get the kids to understand that the work, if they can't explain it to other people, there's really no sense in what they're doing. So communication has to be a big part of the assignment. And that communication can be a lot of different ways. It can be a paper, it can be a blog, it can be a website. I'm about to show you one. It can be a presentation, it can be a video game like I saw in the earlier one. Communication can take a lot of different forms, but it has to be a big part of the assignment. And then finally, and my thinking is really focused on this in that I really, in the last few years, have been focusing the kids on making really quality graphics that don't require lots and lots of words to explain. And I find this really rewarding work and really hard work for them to report the outcomes of a model that they're doing without just writing out all the words, but to be able to put it in visualization. We've been using Tableau for the last couple of years, and I think it's really, really rewarding work, data visualization. Then I also made a list here of some things that I talk to the students about all the time when they're doing these projects. The first one is that thinking through the assumptions is often the most important part of the model. Is what exactly are we assuming to be true, and why are we making those assumptions? Students ask me all the time. We're in virtual learning now, so I'm flipping between breakout rooms on Zoom, and often the kids will, when I get in their breakout room, they'll say, "Can we do blank?" And my answer to them is always, you can do what you want to do, but you have to be able to justify the assumption that you make. And so you have to think through, what assumptions are you making for this model to be true? and you have to be able to justify those assumptions. Sensitivity analysis needs to be central to a student's thinking. In other words, what is the effect of this variable? What happens if I change a certain effect size? How is that going to actually change the results of my model? I find when students make models, they find that if they take a data set and try to fit some model to it, they will find it fits really well until they go to another data set and try to test it on it. Models can be much better at describing than they can at the predicting. And so all of our projects, I try to make, if they're designing it with a certain data set, that they have another data set available for them to actually test and see how it does. Somebody said this, I think Cynthia said this earlier, maybe Greta, that simple models can be just as interesting as complex models. Sometimes my students think it's better if they keep on putting more and more things into their models. And that it often makes, it just makes overfit models sometimes, but B, it makes gobbledygook kind of models. And so simplicity can be just as interesting as complexity. This is a big one for my students, is that they focused all the time on the average instead of the variance, instead of the uncertainty. And that uncertainty or the variance is just as important as the point estimate. In many cases, it's more important than the average that you're getting out. And this is a big lesson that students can learn when they are doing this kind of work. I also find that my students focus a lot, when they have a model, they focus a lot on the significance of the variable, like the p-value of the variable, but they don't really focus often on what the actual coefficient is and what the variance or what the confidence interval around that coefficient is. And so I'm constantly asking my students to think about what was the effect of that model of that variable in this model. How does that compare to the effect of other variables in the model? And what is the uncertainty of that effect size? What's the confidence interval around it?
David, can I add one point to that as well?
Please. Yeah, please.
So in my calculus class, along with that point, what I might do is take that celebrity divorce formula, for example, and I have the kids look up all kinds of constants, like about the age gap between the partners and other things like that they can look up. And then we'll leave one of them as a variable, and we'll do a derivative, for those of you who are in calculus teachers, and talk about marginal change. So that's kind of a different way of looking at effect size, but saying, okay, when this variable changes by 1, if there's one more racy photo of the person on the internet, how does that affect the whole formula? So that's another way to look at this thing about effect sizes within a calculus perspective.
Yeah, absolutely. So I thought I would show you one of the results of a project that we do in class. But this isn't good because my computer is freezing. Uh-oh. Oh, there we go. All right. I told Cynthia and Greta when we were planning this that I can talk about this for 5 minutes or I can talk about it for 3 hours. So I think I have, Maria, about 5 minutes to talk about this before questions. So this is a project I do with my students for elections. I've done it for the last 3 cycles. So I did it for 2020, 2018, and 2016. And what basically we're doing is we're inputting polls into a model. We're creating a model to try to run simulations to predict outcomes in every state. This time we did it in the presidential election. 2 years ago, we did it with this was the one we did with the House election. But this is a really good illustration of what we're trying to do, because if you look at a question like this, like what is the chance of Joe Biden winning Florida, for instance? That's a pretty complicated question to try to figure out. And I start with the kids on what is it that we have to think about? Like, for instance, we have to think about our priors. How did Florida vote in previous years? We have to look at the polls that are coming in. We have to decide how is it that we are going to average those polls. All of these things are decisions that the students have to make. And how they end up making it, I don't always agree with the decisions my students make, but they're going to make decisions. So they make a decision on the priors. And by the way, I talked a lot about communication. This is my students writing on how they decided what they were going to do. So they had a prior about the partisanship of that state, about demographics of that state. Then they took the polls and they developed a way of averaging those polls together. Again, they're trying to explain all that out. Then they are putting in variance into it. How much uncertainty do we have in that? And you can think about some issues like how old are the polls? How many people did they ask? Various things like that that add into our variance. Then you have to figure out how you're going to combine those with the priors and end up with a prediction for that state. But then this particular problem gets even harder because we're not having 50 independent elections. The elections are definitely correlated with each other. And so if you're going to run a simulation, you have to figure out how it is you're going to correlate the states together. And this was, a lot of work in deciding how they were going to do that. And then once they've done that, then they have to code it all and they have to run a simulation. Okay. And we did this. We started in August, and we had our model up and running at the beginning of October. So it took us about 5 weeks. This is a big group of students, okay? All together working on different parts of this. We were in different committees to try to come up with decisions for it. But we were up and running in about the beginning of October. I know I'm in the wrong page here. And we came up with, we had to then make a website, okay? And so we had to display our work. We had to be able to think about, well, what would happen if somebody clicked on a page? What would they want to know about the state, what our prediction is for that state? You can see we were wrong on this one. What we thought that the chances were, how that how our model changed over time as different polls came in over time. I told you we started in October. We were up in October, but we sort of ran it as if we were up in September at that point. So all of this required a whole lot of coding and thinking about what it would be that somebody would want to see when they would click on a certain page. We also did a lot of, after we got it all up, the students all had to write a blog post where they took some particular issue and wrote a short paper, a blog post about what they were looking at. And there are a bunch of these you can see because I had a lot of students. So they were working in smaller groups and each of them had to write that. So this to me is a really good illustration. It was a big deal. It was a heavy lift to try to do this, particularly in distance learning. But if you think about a project like this, you can see all the different things that we've been talking about the assumptions, about the choosing of your variables, about the effect sizes, about communicating your results, about working together. I'm proud of this work, and I thought it was a really good illustration of what math modeling can be if you put kids in a situation where you say, figure it out, that there is no answer, that you have to come up with a model. And then, of course, since there was an election, after the election, we can see how we did. And we talked about comparing our results to, professionals at 538 and The Economist and other people who did similar models to this. And we looked at how our results compared to those and what we could have done differently and where we might have made mistakes and so forth. Yeah, that's the Oracle of Blair. And so here are some resources for problems. This is mathmodels.org and Cubes Hub,
So
which are
mathmodels.org it has a repository of all of the contests from COMAP, and the Math Modeling Hub is a hub for people who are interested in modeling, and it's open to anybody who wants to join. And they're also creating a repository of tried and true modeling problems. So they go through field testing, and they have a writer's workshop for people who want to develop a modeling project, and they can get some feedback. Really interesting group. Yeah.
So we have a couple minutes left if somebody wants to ask questions. Thank you all very much. You can leave that last slide up there if you like the other resources. Yeah, because those are all free downloads. And I put a link for the handbook, but the game report and the computing and communication, those are all free downloads from CIM. If you all have questions or comments that the speakers have given us a lot to think about, lots of great examples of how their students have really, I think, embraced the modeling process. And I mean, it's wonderful to see how each of you has incorporated modeling both in and outside of the classroom. Kind of gives us some inspiration. It's like, will you guys be on the hotline if somebody wants to try something and then they need some help? It's great.
Sure.
So yeah, so we have somebody from China, we have somebody from Oklahoma, North Carolina, Texas. If you want to type anything into the chat, if you have questions or comments, it's just so much to think about. So I'll give you a minute to do that. No questions or comments? It's a quiet crowd. The other thing that I really enjoyed hearing about was how the modeling process and your putting modeling problems in front of your students kind of brings out their own interest. David said, go where the kids have interests, and then bringing in, I think Cynthia, you said something about bringing in their life experiences, or maybe that was Greta, but that idea of agency for students. Oftentimes in school, they don't have a lot of agency. They do what they're kind of told to do inside of sometimes a restrictive curriculum. So both having the idea that we can open the floor to our students' ideas, and also, again, Cynthia, you kind of talked a little bit about how you might incorporate some of those broader topics into an existing curriculum, because we are realistic and know that we are kind of, we have to cover or uncover certain material throughout the year. Do you all have anything else to add to the conversation, the panelists?
I do have one thing I always want to encourage people who are newer. Sometimes you go to these presentations and you see people who've been doing it for a while. And of course, we all like to show great things that our students have done. I would just encourage people not to be shy about trying it, even if your product, is not going to be at the same level as more experienced groups. My school does, for example, the high school competition in modeling every year. And we are just, when we see the results from other schools, we just know we're not in that league, but we aspire and we get a lot out of it, regardless of the fact that our results are just not going to be at the same level as other schools. My students grow, and that's all you can ask for at any level. So please don't think that there's no point in entering a competition if you can't do outstanding work like what you may have seen here. You can do really simple things and the students will still learn a lot and love it.
And I'll echo that and say that,
I just want to make sure that y'all understand that. I think, well, maybe we were okay. Sometimes at 5 o'clock, they cut us right off. So I think we have a little bit more time. You're good. Go ahead, Greta.
I was just going to say that a lot of times, since moving to my new school, we have not had the results that I had at my previous school. It's just different different set of students, different set of level of engagement, but the process of going through the competition, that's really meaningful for the students. They don't think they're going to write a 15-page paper when they start out. And at the end, they've got a 15-page paper that's very well thought out, that they really took time to try to communicate their process and try to wrap their heads around this very messy real world problem. And if we focus on the process of going through this, again, like my students are growing as well. That's where we should be focusing. And you as a teacher will also grow by going through the process and allowing yourself to try things that aren't going to always be successful. You know, I've had a lot of failures in the things that I've tried in my classes, and that's also good to model, you know, because it's not always going to, you don't always know what to expect in a modeling problem as you work through it the first time, and you learn.
I couldn't agree with that. Yeah, I couldn't agree with that more. And you know, at a presentation like this, we're going to share successful things. Maybe we should have another presentation where we share all the things that we tried that just didn't work at all, and all of those things. Even the projects that just blow up, I think the kids really they learn from it and they get better. I found that kids in 9th grade start this and have no really idea what they're doing. By the time they get to 12th grade, they're really into it. They get better as they go along. And so I wouldn't worry at all about, you know, winning competitions or things like that. I would worry about them having the experience in high school of dealing with these kinds of problems, and then developing their own skills over that period of time. And it's really valuable for the students and for the teacher. I couldn't agree more.
Great. Thank you. Thank you for those comments. Like you said, David, we'll think about a webinar with showing our next time.
Yeah, I got a lot of slides for you, Maria.
Oh my goodness.
I think we each need our own separate webinar for that.
Yeah. And also we'll have the video recording of this session and the slides available on the mathmodels.org website for those of you who are here, and also for your colleagues. You can share that with colleagues. We have one more webinar coming up. It's in this school year. It's our 7th webinar on May 12th at 4 p.m. And we're going to have Matthew Felton-Kostler talk to us about some math modeling projects that he's done with middle schoolers. His talk is called From a Living Wage to School Segregation, Middle Grades Modeling to Understand the Real World. So I want to thank all of you for being here with us, both the participants and our panelists. We really appreciate you taking time to share your experiences in math modeling and to encourage us all to, you know, dig in and try, you know, just start something small if you've never tried it before. And thank you all very much for getting some love from our folks in the chat. And I'm grateful. Thank you, COMAP, for sponsoring this webinar series.
Thank you, Maria, for organizing.
Yes, you're welcome. Thank you all so much. It was really fantastic to hear about your experiences.
All right, bye-bye.
Thank you.
Bye. We'll sign off.
Thank you, guys.
Yep.